So today we continue to work with point processes, and we will study a very important notion of factorial measures and factorial moment measures of a point process. And to understand the idea of this concept, I propose to start from some example, and we consider a point process on Z. So this is very simple example, which will show us the main idea of factorial measures. So we start with example of a point process on Z. So it seems that it's easy to understand what is it. So we have numbers 0, -1, 1, 2, and so on. And we assume that we can find a particle on a point of Z with some probability. So we have a particle or don't have here, empty. And we want to understand how we can describe the distribution of such joint behavior or joint appearance of a particle in such a system. So to define the distribution of existence a particle, we can define the following probabilities. So I would like to define distribution of measures. So I will say that we have the measure mu that are of the following form: xi, I in Z, and here xi some points from Z. So we have here on this example, on my picture, I have delta measures of delta 0 plus delta 2. It's for example. So how we can define the distribution of such a measure? So to do this, actually, we need to define the distribution. So this is the same that define distribution on sequences of 0 and 1. So we can formulate the description of the picture that if I can see here a particle, this means just 1, and if not, I have 0. So for any measure of such form, I can put into the correspondence a sequence of zeros and 1 of such sequence where I have values 0 is 1. And to do this, maybe you can recall from the stochastic theory that the theory of stochastic processes, that in order to define the distribution of a process, you need to define its finite dimensional distributions. So to do this, I will write such correspondence to this. We need to define the following probabilities that define probabilities of the form. Okay, if I have y at position minus n is equal to some value. This is 0, 1, minus n plus 1 is equal to plus 1, and so on. Y0 is equal, and so on. So yn is equal to epsilon n, where epsilons some sequence of zeros and 1 fixed and with values 0 or 1. So you can recognize here the finite dimensional distribution of the sequence. So if I know all these probabilities, then I know whole distribution of sequence, and this means I know the distribution of such measure. So this is the same. And we can write these probabilities not considering just 0 or 1s, but I can consider the following probabilities. I can just consider only that points which contains a particle. So this is the same as if I define the following probabilities, that for some fixed points, how to know them, some fixed, okay, z1, z2, and so on, zm. If I define the probabilities that measure at these points is equal to 1, mu from z2 is equal to 1, and so on, mu from zm is equal to 1. Why is it so? Because if you know such probabilities, you can find all probabilities of this type. So indeed, just here you can use the principle of inclusion conclusion. So for example, if you have the probability that some y0 is equal to, for example, 1, y first is equal to 0. How you can rewrite this probability? Just using these probabilities, this one. So just need to write the probability that mu from y0 is equal to 1 and minus probability that mu from y0 is equal to 1 and mu from y first 1 is equal to 1 also. So you using such probabilities, you can find all probabilities of finite dimensional distribution. So the main idea of this story is that it's enough to consider such probabilities. So we just interested in the probability that at some fixed points we have a particle. So this is the main idea which leads to the factorial moments. And how we can see this? So let me write the following. So let us consider this event by itself. So I consider event that, not event, just indicator of such event, that I have mu at z1 is equal to 1, mu from z2 is equal to, I will write essentially mu from z2 and so on, mu from zm is equal to 1. And if I consider them, I recall that for a measure mu of the form delta sum at the point xi, I from z. So I have these points, and let me. I'm sorry, I for now do not need this one. Let's consider step by step. So if I will sum the indicator of the following form, that mu of xi is equal to 1, and I sum over all x's in some subset B. So, okay, I have a line, and I count only those particles which are in subset B. So this is just my measure mu of B. Now, if I consider summation over integral of indicator that I have two particles now, because here in these probabilities I considered events that at several points I have a particle. So I consider x dot is equal to 1. And since my finite dimensional probabilities are defined for non-equal points, so here I will write that my points are not equal, then, and I consider all points in subset B. What will I have here? So if I sum all these indicators, we can rewrite it in the following form. So at first I can consider all indices without this assumption that they are not equal. So I write B indicator that mu of x I is equal mu of I. For purpose, I will write as product mu from x dot is equal to 1. And I should write minus those part where I is equal to 0. So I just write one index indicator that mu of xi is equal to 1. Xi. Okay, so here you can recognize the product of two sums. So I just write mu of b times mu of b. And here again, mu of b. So we get not the product of, not the square of measure mu, but such form. Okay. So here we can continue this consideration, and let us formulate it like our proposition. It's just a combinatorial one. For now, we do not have some probabilities and so on. So we have a measure for measure mu of the form delta x I from z. If I consider summation over non-equal indexes, I2 not equal I m, such that x all they I L in subset B, and I consider all these indicators. Mu of xi first does not equal mu of x, I'm sorry, equal xi2 equal and so on, mu of xim is equal to 1. Then in answer, I will get the following: mu of b times mu of b minus 1, and so on, times mu of b minus m plus 1. So this is just what we can observe, and I think the proof is just by proof you here need to use mathematical induction. We did the first step, and the main idea we saw on this consideration. We just need to rewrite this sum and split the last inequality in summation scheme. Okay, I just can write it. We write, so if we know this for m minus 1, then for m, this sum we will rewrite. We use here m minus 1 index, and here at the last sum, I just write here overall index im minus 1 minus all possible values where im minus 1 belongs to the previous one. First, oh, I'm sorry, here, just m. im belongs to all previous. So using this quality, you can easily get this result. And now let us take the expectation of this equality. So take the expectation, and we will have just taking the mathematical expectation of equality from the probability from the previous proposition. In the proposition, we get that, okay, I have sum over non-equal indexes im. Indicator becomes the probability that mu of x I equal to 1, and so mu of x m is equal to 1, and all these points belongs to some subset B. Here we will have the expectation of this expression, so I just rewrite it. Mu of b, mu of b minus 1, and so on, mu of b minus m plus 1. Okay, and this what we have in the right hand side. This we will call the moment of factorial measure. So let us give the definition. So we'll give the definition of factorial measure and of moment of factorial. So, and we start with the, for now, we'll start for the, from the factorial measure for a point process of this form, where we have just sum of delta measures at some points. So let's start. Consider for measure. So now this is not for process on Z. This was just for explanation. So now for a point process on some space X, we have some space over the form mu delta xi, I from 1 to some k. K here can be as natural number or infinity as well. We define a factorial measure as following. So we have for any m, so this will be the power of, let me write here, m factorial measure, and subset of C in product in this product, I will define the m factorial measure of a process mu by this equation. This is the sum over non-equal indexes, like we had in the left-hand side in the proposition, and here indicator that. So I will write not in the term that mu of x I is equal to 1. I will just write that points x I and so on. So I m. So this is m-dimensional vector. It belongs to subset C. Okay. Let us consider small example. So when m is equal to 1, this is just m is equal to 1. We have just mu of C is equal usual mu of C, because this is okay, let's write sum of indicator of z points that belongs to C. This is mu of C. Now when m is equal to 2, let us understand that this is we already considered this. So from our proposition, this is just mu from C minus 1. So how we can understand this on the picture? So on the picture, we want to define some product of the measure. So I draw a product of the space, and I have, let me write something like this. So I have these points in my point measure. And I count not all points in the intersection like we usually do, not all points in the product of space like here. But I take into account only those with different indexes. So this one I take, but this one I do not take into my consideration. So if this is subset C, this one, subset C, then second factorial measure is equal to this one. So we have just we take into the account all points in the product just without diagonal. Okay, so we define here. I'm sorry. C. It's better considered not like C here is a product here, A times A times A. So for such subset, I draw a picture. And maybe this is not good notation because of this one. Here I have C of the form A times A. But if I take for C, this is a continuous example, for C of the form A times B, so this is just some rectangular, I will have the same picture A times B. What is it? So we can just draw the picture and see what we have. If I have here points and so on. And let me take for subset A this one, and for subset B this one. So for here, I will consider all points that are of diagonal. So this one, this, and this. And this that are on diagonal, I don't consider. So how we can count them? You can check that this is just a measure of A times measure of B. So I take the just all points count and minus, what should I minus? The measure of intersection. So what do how many points do we have on a diagonal? As much as we have joint points in sets A and B. So this is the form for second moment, for second factorial measure. Okay, so now when we understand how we can define M factorial measure, so we just write in this way, and let me write once. Now we can define the moment of factorial measures, and this is also for definition. Define now factorial moment measure is just the expectation of factorial moment. So I just write for notation alpha m of subset C is the expectation of factorial C, where C is from M's product of the space. Now maybe so for simplicity, let us write down the okay, no. So we can use the notation. So it's just notation. We will use later. So if I have the number, just A from, and then I can write its product that we had before of this form, A minus 2, so on, A minus n plus 1. So I denote this just the definition by A to the power m, but with such square brackets. So this is for notation. So this is so-called factorial power of the number, and that's why we have this notation like a factorial moment of the measure or factorial product of them. So now it turns out that these factorial moment measures define the point process in almost all cases. So what do I mean? Maybe you know from the probability theory that under some conditions, all moments of a random variable can define the distribution of random variable. Yeah, but you need to assume some conditions, of course. And here, the same idea we have for point processes, that for a huge class of point processes, the factorial moments, this factorial moments measures define the distribution of a point process. So this is like, why do we need them? And the question is about why we don't use just the usual product of measure. This is because sometimes it's not so good to consider the diagonal. So here, when we consider this sum with non-equal points, we saw that such probabilities describe the distribution of the point process on Z. But here we assume that indices are not equal. So it turns out that it's much more easier to work with summation over non-equal points for point process. And this is as exercise for you for homework. Thanks. So let's try to find the factorial moment measure for a Poisson process. Find, okay, let me write if let nu be a Poisson point process with intensity measure lambda. Okay, then find factorial moment measure of, so this is like exercise for you. Okay, so what do we understand for now? That if I have the sum of such probabilities when I consider not equal points, then this is equal to expectation of factorial power of the measure mu of subset. And this is okay. What we have now. Let us understand if I have just a function, just consider a function on x to the power m. So I have a function that have m coordinates x I first, x I second, so on x I. And again, if I consider the summation over all indices that are not equal, and take the expectation, then this can be written using the integral over x m of this function. Let me write y. So this is the coordinates of integration, and here I write this factorial measure alpha m, d alpha, alpha m of d y first, d y. So why is it so? Here we just need to use the definition of our product of factorial power, and the idea of proof is the same as we had with the Campbell formula. You just need to write the step approximation for function f. So this is not hard to see, and I will write it as exercise to prove this equality. This is very easy, and it follows from the definition. Prove this equality. And now I want to go further and present you the assumptions under which we will have the uniqueness of distribution of a point process if we know its all factorial moments. So now let us consider this question. Okay, if a question for now, if I have two measures or measures, okay, I will write for point processes. Point processes. eta and eta prime, we know that their factorial moments are equal. So I will write moments are equal. Will we have that these points point processes have the same distribution? And to answer on this question, we will need the following proposition. So what is the idea, how we can prove this? The idea to answer on this question is to use our criteria from the second lecture, I believe, where we consider the criteria for equality in distribution for processes, and there we have that two processes are equal by distribution if their Laplace transform will equal. So I will write equal by distribution if and only if what for any positive function from x to r plus, we have that their Laplace functions eta of u is equal to eta prime. So this was the second lecture. You can check this. So now the idea that how we can represent this Laplace transform for a point processes using just factorial measures. And for this, we will see that we can compose into a series some special Laplace transform. So let us formulate this like lemma, the following result. So let eta be a point process on x, and we assume that for some subset B, there exists a constant C that is greater or bigger than 1, such that a factorial measure, this is factorial measure of b to the power n, so that this is just the usual product of the set, is less or equal than n factorial c to the power n. So here we can see that this is the assumption on how fast the factorial moment measure can grow, not faster than n factorial times c to power n. And now we take a function that is x from x to r plus, non-negative function, and a constant a less than 1 over c, such that this function is bounded by the constant u of x less than a for this subset B, for all x in B. And u from x is 0 for outside of subset B. Then we will have then the expectation of exponent also here, integral over x logarithm 1 minus u of x. This integral with respect to our point process nu dx. So such exponent will be written in the form of the following series. So here we will write the series from 1 to infinity, minus 1 to the power n factorial, and here integral over x to the power n. Here the product, okay, let us u from x1, u from xn, and here the factorial moment factorial measure of our point process dx1 dxn. So what we have, if I take some specific function here, so maybe you can recall that in the Laplace transform we have here just some arbitrary function v for example. So you can but if we take logarithm 1 minus u, then we can represent this expectation like series of just here product of the functions u with respect the integral with respect to factorial measures. And this is the main idea that we will use later to prove the uniqueness of the distribution, because if we have the equality of factorial moment measures, then under some conditions, so we know what conditions, the series converge and the Laplace transform will defined uniquely by factorial moments measures. So let's try to prove this lemma. And to do this, first we will note the following. So if I have the following, so this is just for measures. For simplicity, we will consider the measure of the following form. For measure of the following form, so I have just sum of delta measures, and I take u that x from x to r, just some measurable function, and I will consider the product of 1 minus u of x I from 1 to k. So I just take the product over all points here. I consider all points, and I consider this product. So let's try to see that this is equal. We can represent it using the factorial, the integral with respect to factorial moments, not moments, factorial measures. And factorial, and here integral u of x1, u of x n, this one. And here I write the factorial measure n dx1 dxn. And then what we need to do, we will take the expectation of this two. So this is the main step. So here you can recognize how we can represent, find the, if we have the series of integrals with respect to factorial measures, then we have this representation. So how to prove this? Just we'll use using mathematical induction. So if k is equal to 1, k is equal to 1, actually this is obvious. So I have one point here, just one, and here, if I write down here, I will have one summand minus 1, and integral with respect to measure itself is just u of x. So this is true. Now let us consider, suppose that we know this proposition for k minus 1, k minus 1, consider for k, for k. So I will split my point. So I have a point process here, delta x I from 1 to k minus 1 plus delta x k. So I will have sum of 2 points point process. And let's consider this. So this is just a simple calculation. 1 minus u of x I from 1 to k. Okay, I split it to 2 parts. K minus 1. So here I will use the formula for known result, and times minus 1 u from x. Okay. So here just we need to rewrite this using this expression in terms of integrals, and this integral I will write using summation. So using the step of induction, I write 1 plus here summation from n1 to k minus 1 and factorial, and the integral I write just using what we considered before, just summation with non-equal indices, and they are not equal to k. Not equal to k, because we consider here just k minus 1. Here write u x first, u x okay, this is by step of the induction. This is first, and u of x k. So now if I just open the brackets, and we need to understand that we have the same what is stated in the lemma, not in lemma, in this first step, in this formula star. So here, when n is equal to 1, okay, I will write k minus 1 plus 1 and factorial 1 multiple in u of x I first, u of x in, and here minus u of xk, and here let me write also minus 1 to k minus 1 and factorial. And now here the same, but this is times u of xk on u of x in times u of xk. So we just need to reorder these terms, and you can see that for actually we have the answer, but you just need to put them together. So for n is equal to 1, I have this summand, and I will group with this n is equal to 1. So at total, I will have here the summation for minus 1 to the n and factorial. So when n is equal to 1, I will have all summands of such form, u of x I n. So why is it so? So for n is equal to 1, we have, I take from this one, and here I have just not product, but summation over all indices that is not k. When in this summation n is equal to 2, then I take here the product for indices that are not equal to k, and plus from this sum I take for n is equal to 1, because I have product by uxi times uxk. So I will have the same summands. So you can check that this is the same. Okay, when we have this nice formula, then we can apply it to our case. Indeed, what do we need? This is the second step of the proof. And in order to, first we write the expectation of integral. What do we have? Integral of x1 minus u of x mu dx. I write it as summation first. I write this integral as sum, because let us continue considering this one from for infinity. So here I omit some technical details how we can get from this type of measures to a general class, but I think it's a technical details, and here we just need to understand the idea of the proof. So I write this as sum over u of xk xi, take I from 1 to infinity. Oh, I forgot logarithm. So this is just the product of expectation into logarithm. I will have 1 minus u of x. So that's why we consider such a strange form here, just in order to obtain this nice representation from the first step. So here I have 1 plus, and here the sum I from n from 1 to, I will write to infinity, and here 1 to n factorial, and here the integral u of xi. Let me write the term of y first, u from yn, and factorial power d. Okay, and now what do I need to consider? Now I write the expectation. I write the expectation here and here. So when I write the expectation, then this means that I change the just factorial measure to its factorial moment measure. And from 1 to infinity, minus 1 to n, and factorial, and here integral alpha n of dy first, dy. And here now we need to understand why can I. So I did this step, but I did not explain why I can change the order of summation and the expectation. Let us understand why does this integral converges absolutely. So we can write the upper bound for this integral, alpha n dy first, dy n. So I just write that this is not equal, and I write the modulus here. And by assumption, what do we have? Let us recall. We have that the function is bounded by a constant that is less than 1 over c, and the factorial measure of and important that a function u is 0 outside of subset b. So we can consider this integral just on subset b. I will write. So here the upper bound for u is 1 over c to the power n, because I have n, and here alpha n of b to the n. And by our assumption, this is less than, what do I have? 1 over c to the power n and factorial c to the power n. So I have that, just a moment. Just a moment. Here we have less a. So let us write this, not c, but we will write a. So I have c over a. And when I substituted here, since A is smaller than OC, since A smaller than C, oh, just a moment. Let me not like this. Not me. Don't hurry here. My function u less than a and a less than 1 over c. This is what I want to write. So we will have that the series converges then a times like this, yes. Then a times c less than 1. So we have that this series converges absolutely, and so we can change the order of expectation and summations. And the series. So we can see that from this, so this will end the proof. And on the next time, we will do last small step to understand that this is enough to prove that that this condition almost enough for uniqueness of the point process. So for today, what we done, at first we introduce the concept of the factorial moments, and we understand how they connected to summation of a function for non-equal points of a point process. And we saw that the factorial moments can uniquely define a point process under some conditions. So this condition is not so strict, as we will see from practical questions later. So this is all for today's lecture, and if you have questions, you can ask.